Welcome to 15.3 vectors in a plane. We are mainly going to be focusing on operations as well as focusing on unit vectors as well as how to work with different types of vector problems. In slide 2, we begin with understanding what is ultimately going on with a vector, the direction that it faces, as well as what would occur as we start multiplying our way through a vector problem. So as we start taking a look at the image that we have here, when comparing the different vector arrows against each other, ultimately they are all facing the same direction when we start off with V. Now, as we start multiplying our vector, our V, against various numbers, notice we multiplied V against 1, that's our initial arrow, which is here. Now, we also multiply it by half. Now, there is a direct relationship between when we multiply by a number and that vector. So when we do multiply by half, we do end up with a shorter vector, which does mean that a vector will have a direct relationship with its length as well as what it's being multiplied by. In our third example with 2v, notice the length of our vector has doubled in size. As we begin to start multiplying by negative numbers, notice it's not like a slope. It does not aim downward towards the right-hand side. That line remains the same. The only difference is the arrowhead goes from the upward side of the line to the downward side of the line. And the easiest way to determine that would be through our first V and our negative V. Taking a look at those two will help you kind of understand where the arrowhead is pointing to determine whether it is positive or negative. If it's facing up, it would be positive. If it's facing down, it would be negative. Same thing would happen with our last example, which is a negative 3 over 2v. Notice in this case, we are basically multiplying by 1.5. So our length of our vector would get longer, but it will be facing in a downward direction as far as the arrowhead. In this slide, we go ahead and talk about tail to head, as well as the parallelogram representation and understanding how everything comes together. In example A, we go ahead and we talk about tail to head. And in this case, what occurs is as we start adding our different vectors and we add u and we add v, they will always have the end of one vector starting with another one. And when both are added together, that gets you from the initial point all the way over to the end. Now, in the case of a parallelogram, you will still have multiple parts of a vector, but what will occur is that they will go in different directions, and when you add them together, they go down the middle to the same endpoint that you would have when looking at our parallelogram. Keep in mind, in a parallelogram, different sides are congruent. So in this case, if we were to look at V, our V here would be equal to V being here, which at the end of the day is almost very, very similar to what we were doing before with tail to head representation. In slide 4, we go ahead and we start taking a look at some of the operations that we were dealing with. So in this case, we are looking at sum, which in this case would be our u vector plus our v vector. Now, as we can see, we have u1 and u2. With v, or our vector v, it would be v1 and v2. The positioning of the u1 and the u2 is almost very similar to an x and y position. So it's kind of like an x1 and y1, and our v's would be kind of like an x2 and y2. Now here what would occur is that we would add our x1 and x2 from each one vector and combine them together. So this would equate out to the same as our pointed parentheses x1 plus x2 comma y1 plus y2. Now keep in mind this would occur the same way with a subtraction problem or a difference problem. As we go ahead and we start to take a look at our product of scalar, in this case we can see that k, which would represent a number, would get multiplied by our u vector. Now when this occurs, k would be multiplied against each one of the terms that is within the vector. So a great example of that would be if we had a vector of 1, 2, and we were multiplying by 4, being our k. In this case, we go ahead, we distribute that 4, which would leave us with 4, 8 as our vector. Please keep in mind, remember, our vector will always be represented with our pointed parentheses. In slide 5, we have various examples of different operations that we would be able to see, whether it's addition, subtraction, possibly even a little bit of multiplication involved within this slide. Here we have 3 problems to be able to work with, which would be A, B, and C. As we scroll a little bit further down, notice the solution for each one is there. As we take a look at the very top portion of this slide, our V and our W vectors are being given. So in this case, we are going to want to go ahead and start off with our first problem, which is 2v. In this case, we would go ahead, we would multiply 2 times -2 and 2 times 5, which would leave us with a -4, 10 as our answer for 2v. As we take a look at our second problem, we have w minus v. Now, keeping the order of a problem, especially with subtraction, is extremely important. In this case, our first vector would be 3, 4, and we are subtracting -2, 5. The same process would be done. We go ahead, we grab our first number, which would be 3. And as we grab that first number of 3, we are going to subtract a -2. As we're subtracting that -2, that's going to leave us with 3 minus a -2, which would cause that -2 to turn into a positive. 3 plus 2 would leave us with 5. We repeat the same process with our next set of numbers. So 4 minus 5 would leave us with a -1. So our final vector here would be 5, -1 for the w minus v. Now it's always important to go ahead and write down what the problem is, because we do not want it to be associated that we're trying to say that v is equal to a certain vector, or that w. In this case, we are adding or subtracting w minus v as that vector. The solution or the result of it would be w minus v to equal our 5, -1 vector. As we take a look at slide 6, we do cover our last sample problem, which in this case was v plus 2w. Now in this case, we do want to go ahead and kind of do our order of operations, where we are distributing 2 to 3 and 2 to the 4. That would leave us with 6, 8. We are then going to go ahead and add -2 and 6 to give us a positive 4. And we're going to add 5 and 8 to leave us with 13. Now, it did ask for us to go ahead and graph our problem. Now, depending on whether you wanted to go with the tail to head method or parallelogram, it would directly result in you coming up to the same answer in either case. Let's go ahead and take a look at slide 7. So in slide 7, we have 3 problems. What I would suggest, go ahead, pause the video at this point, work on this slide, and we'll go over it in 1 minute. So taking a look at slide 7, we start off with u plus v. In this case, we have our u would be -1 plus 4 comma 3 plus 7. Here we would end up with 3 comma 10 as our vector for u plus v. In the case for b, we're going to multiply 3 times our initial vector, which in this case would be a -1, 3. So 3u would be equal to -3, 9. Lastly, we have 2u plus a -1 times v. We begin by putting in our vectors into our problem. So 2 times -1, 3 plus a -4, 7. First thing that we want to go ahead and do is multiply that negative into the actual problem itself. And what's going to happen is we are going to end up with a -2, 6 as our first vector, or the first part of our vector, plus a -4, -7. As we add our 2 digits together, being the -2 plus the -4, that would leave us with -6. 6 plus a -7 would leave us with -1. That would be the answer for our 2u plus -1 times v. Let's go ahead and take a look at slide 8. Now, in slide 8, we are taking a look at our vector u and how the absolute value of u is equal to 1 unit vector. Now, this is pretty important because it helps us to have that understanding that we will have a single vector of u, and we would go ahead and write our vector on the top over the absolute value of v, or of that vector underneath. Easiest way to take a look at it would be through example 9. Now, in slide 9, the one thing to remember is that our double absolute value of v, that is very, very similar to what we covered at the very beginning of this section, which was the absolute value of v is equal to the square root of a squared plus b squared. So as we start finding out what this problem is going to look like once we're told that we have to find a unit vector that goes with the direction of that specific vector, we first place our vector in the top of our fraction. So we have -2, on the top. In the denominator, we're going to grab our a and grab our b, and we are going to square each one of the numbers. So in this case, we would grab the square root of -2 squared plus 5 squared. So negative 2, 5 over negative 2 squared would be 4 plus 25. And we're going to get the square root of that number. Once we've done that, we're going to go ahead, simplify this out. Our denominator would then be the square root of 29. Numerator would be negative 2, 5. Now, what we can do at this point is go ahead and divide each one of the numbers within our vector by our denominator. So as you can see, our answer would be directly below as a vector of negative 2 over the square root of 29, comma, 5 over the square root of 29, close the vector off. Now, we do have the ability to go ahead and rationalize the denominator, but it would be perfectly fine to leave it with the square root of 29 in the denominator. It just depends on what we are covering within that given section. Let's go ahead and take a look at slide 10. In slide 10, we do begin with the same similar problem that we did previously, which was to find the unit vector in that same direction, but we also have to verify that it has a length of 1. So in this case, what would happen is we would start off with our general equation of v over the absolute value of v. So our vector, which is negative 3, 2, over the square root of negative 3 squared plus 2 squared. This would leave us with negative 3, 2 over 9 plus 4, which is the square root of 13. Now we are going to divide each one of our numbers by that square root of 13. So we have a negative 3 over the square root of 13, comma, 2 over the square root of 13. And that would give us our vector. We do have to verify that it has a length of 1. So we're going to go ahead and we're going to re-plug it in to the denominator that we have. So as we re-plug it in, this would give us a negative 3 over the square root of 13 being squared plus 2 over the square root of 13 being squared. This would leave us with 9 over 13 plus 4 over 13, which is 13 over 13. So the square root of 1 gives us a value of 1. In this case, since we do end up with our value being 1, we have concluded and verified that the length is 1 for this problem. Keep in mind, we are plugging our vector in to our equation of the square root of a squared plus b squared in order to determine if it has a length of 1 or not. In slide 11, we go ahead and we start talking about different forms that we can see the information being given. Now the first form would be in component form, which in this case would be with our pointed parentheses around our a and b value. And we also have standard form. So in the case that this would be a 5-3 scenario for our a and b, this would be similar to going ahead and writing our a, which would be 5, and writing I directly next to it. We then have a positive 3, which would leave us with plus 3j. And that would be writing it in standard form. If our 3 or if our 5 was negative, we would put the negative in front of the 5 or the 3. In this case, if it was a 5 negative 3, we would have 5i minus 3j. Now this can be done for any type of problem that does have a vector as a final answer. Let's go ahead and take a look at slide 12. Here we have an initial point and a terminal point. So we're going to go ahead and determine what our vector would be. In this case, we are writing u as a linear combination of the standard unit vectors of I and j, which means that u would be equal to a negative 1 minus 2, comma 3 minus negative 5. We go ahead and combine our first two. Negative 1 minus 2 is the same as negative 1 plus a negative 2, which would leave us with negative 3. And 3 minus a negative 5 would leave us with 8. And that would be equivalent to our u vector. Now keep in mind, this would be our component form. Now, if we were going to go ahead and put it into standard form, we would write it as u equaling negative 3i plus 8j. And that would be our standard form. Our last slides in 13 and 14 is a summary of the various problems that we have taken a look at throughout this section. In this case, you can go ahead and see how it is that we would go ahead and find the component form of a vector. Notice we would do our terminal point minus our initial point, which would be q1 minus p1 and q2 minus p2. That would give us our final vector of vector 1 or v1, v2 as our final answer. We also go ahead and go over the magnitude. Now this should look somewhat familiar because this is the absolute value of v, which in this case it is the same as what we just did above. We are subtracting our q1 minus p1. We're going to square that, plus q2 minus p2, and squaring that. This can also be seen as a squared plus b squared, and getting the square root of that entire problem. Keep in mind, if our entire vector is equal to 1, then it is a unit vector. This was similar to when we were completing the problems on, I believe, slide 10, when we not only went ahead and solved for the vector, but we also plugged it back in to determine if it equaled to 1, then it was a unit vector. In slide 14, we go ahead and take a deeper dive into our different operations. Now keep in mind, even though we are only looking at sum and multiplication here, the same process can occur if u minus v were to occur. Now in this case, this would just be u1 minus v1, comma u2 minus v2. And when we are multiplying, just keep in mind we are distributing the k. As we work our division problem, keep in mind anytime that we divide by a square root, we do have to divide each one of the vector numbers in the numerator by that square root number. We do have the ability to get to rationalize the denominator, and if we wanted to move a square root up to the numerator, we could, Or if you have other instructions from your teacher, you can go ahead and do that. So for example, if I decided to go ahead and keep it as, instead of, let's say, a vector of -2, 4, that's being divided by the square root of 11, we could go ahead and say -2 over the square root of 11, comma, 4 over the square root of 11, and have that as our vector. Keep in mind, we could also go ahead and rationalize the denominator and say that this would be a -2 square root of 11 over 11, comma, 4 square root of 11 over 11. Now this would be in component form, but we do have the ability to also change this into standard form. So this would be the same as writing our problem above as -2 over the square root of 11 I plus 4 over the square root of 11 j. And if you were rationalizing, it would be the same as -2 square root of 11 over 11 I plus 4 square root of 11 over 11 j. If you have any questions on any of the operations, feel free to reach out at any point.